Hello, everyone, and welcome to our webinar. My name is Warren Hamrick, and I'm an Engineered Wood Territory Lead for APA. I'm going to serve as moderator for this session, and our main speaker today will be Noah Humberston. Our topic today is titled Mastering Wood Structural Panel Design and Specification, and is based on APA's Panel Design Specification Form D510. This webinar highlights important considerations and valuable resources for designing with wood structural panels. Two examples will showcase the proper design of wood structural panels for different structural applications. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood construction systems and educate users and specifiers on the product's proper use and potential applications. Before we start today's webinar, I need to cover some housekeeping details. This presentation will last about 55 minutes. Handouts of the slide can be found in the control panel on your screen. To ensure that everyone can hear the webinar clearly, we have muted all participants. And while we are bookending the discussion with our cameras on, we're going to be turning them off during the session to maximize the connectivity of the webinar. During the presentation, we encourage you to submit questions by typing them into the question pane on your control panel on the screen. We will answer some questions in the chat box, and we will also answer some in a Q&A session at the end as time permits. A recording of today's program will be posted on our website, apawood.org, in about a week to give a further opportunity to review content or share with others who are unable to attend today's session. I'd also like to note that today's webinar is approved for continuing education credits, including AIA and ICC. About an hour after the conclusion of the webinar, an email will be sent to each attendee. It will include a link where you can get customized certificates of completion. The information provided on this webinar is based on APA's research and field experience, but no warranties expressed or implied are made. APA and its members are not liable for any damages resulting from the use of this information. Users should consult local regulations or a design professional to ensure compliance with relevant codes and standards. APA does not control workmanship quality or usage conditions, so it cannot guarantee product performance or design outcomes. The content is copyrighted, and reproduction or use for AI training requires written permission from APA. Your feedback is important to us. I would like to point out that you can see a QR code on your screen. If you open your camera on your smartphone, a link will pop up to take you to a survey on this session. A link will also be emailed to you about an hour after the conclusion of the webinar. At this time, I would like to introduce you to our presenter today, Noah Humberston, Engineered Wood Territory Lead for APA based in the Philadelphia area. In that role, Noah works with designers, building officials, and builders to provide construction and design direction for the use of APA member company engineered wood products. Prior to joining APA, Noah gained 4 years of structural design experience working at a leading engineering firm. And in this role, he worked with both national and regional builders in the design of residential structures using engineered wood products. Noah is a graduate of the University of Delaware with a BS in civil engineering and is a registered professional engineer in the state of Pennsylvania. For those of you just joining us, welcome to our webinar titled Mastering Wood Structural Panel Design and Specification. Noah and I will now turn off our cameras to facilitate our presentation, and I will now turn the program over to our speaker, Noah Humberston.
Thank you, Warren, for the introduction, and thank you to all those joining us today. In this session, we're going to take a deep dive into specification and design of wood structural panels, or WSPs. We'll focus on 2 key APA resources and how to use them effectively. These resources are APA's Panel Design Specification, Form D510, and load span tables for APA wood structural panels, Form Q225. We'll cover important details like the properties of plywood and OSB panels, how to interpret APA trademarks, and what to look for to ensure code compliance. A big part of this is understanding how to apply design values correctly when specifying panels for structural use. To bring everything together, the course includes 2 real-world examples, one for designing a heavily loaded roof and another for wall sheathing. Here's our learning objectives for today. We'll start with wood structural panel composition and standards. Then we'll look at their mechanical properties and how design values are adjusted. We'll apply APA's panel design specification and load span tables. And finally, we'll touch on key design factors like nail withdrawal and pull-through that affect structural performance. Engineered wood can be summed up as any wood-based building material that has been enhanced through a man-made process. Generally, these can be divided into 2 categories, panel products and framing products. Let's look at framing products first. I-joists are formed with a top and bottom flange composed of sawn lumber or structural composite lumber, with an OSB web connecting the 2 flanges. Glue laminated timber, often referred to simply as glue lam, is composed of various layups of sawn lumber. Then there's structural composite lumber, or SCL, which is actually a group of products composed of wood veneers or strands and includes laminated veneer lumber, oriented strand lumber, laminated strand lumber, and parallel strand lumber. Glulam and SCL products have a range of structural applications, including beams, headers, columns, and studs. Finally, we have cross-laminated timber, which is a heavier panel product most often used in mass timber construction. The focus of our webinar today will be on wood structural panel, which includes OSB and plywood. Plywood has ancient roots, with evidence of laminated wood found in Egyptian tombs, and similar techniques used in China, Europe, and Russia over the centuries. The first plywood patent was granted in 1865. APA was initially formed as the Douglas Fir Plywood Association in 1933, and later renamed to the American Plywood Association, before expanding our membership to manufacturers of OSB and other engineered wood products. The first version of oriented strand board was invented in 1965. During the 1970s, the plywood lumber supply dropped. OSB became much more popular and was first qualified by APA in 1981. Over the years, panel products have expanded to include more specialized products that include siding and specialty panels such as radiant barrier, formwork, industrial panels, and overlaid panels. While this isn't our main focus today, I'd like to take a moment to highlight the sustainability benefits of engineered wood. Wood is a naturally renewable building product. In fact, more timber is grown than harvested each year in North America. We all know that healthy forests play a crucial role in absorbing carbon dioxide out of the air, which helps combat climate change. What's even better is that carbon stays locked away, not just in the trees and soil, but also in long-lasting wood products, including engineered wood. One key advantage of engineered wood is that it can be made from smaller dimension lumber, which makes better use of available wood resources. Plus, by strategically layering different wood species and grades, we can achieve greater structural strength with less material. Compared to other common building materials, producing wood-based structural products requires significantly less energy, making them a more sustainable choice. If you're interested in learning more, see APA Form F305 titled Sustainable Buildings, Sustainable Future, available for free download on the APA website. Both the IRC and IBC require wood structural panel sheathing used for structural purposes to conform to the Department of Commerce PS1 and PS2 standards in the US, or CSA 0325 or 0437 when used in Canada. These Department of Commerce standards ensure consistent quality, strength, and performance. There are 2 key standards to know. The first, PS1, is a prescriptive standard for structural plywood, covering wood species, grading, adhesive bonds, panel construction, dimension tolerances, moisture content, and more. PS2 is a performance-based standard that applies to both plywood and OSB. It focuses on how the panel performs rather than just how it's made, meaning different manufacturing techniques can be used as long as the final product meets the required performance benchmarks. Note that the APA panel trademark will identify compliance with these standards. I'll review additional information that can be found on this trademark a little later in the presentation. Before we dive into the composition of plywood and OSB, it's important to understand some wood science principles. One point to understand is that wood is strongest in the direction of the grain, so the way it's loaded matters. Wood strength also varies among different species and grades. Therefore, the construction and layup of panels impacts the panel's strength. These variables are addressed in the PS1 and PS2 standards and are used to develop the span rating of the products. In general, though, the more wood or the thicker the panel, the greater the strength. Let's start with plywood, which is known as the quote-unquote original wood structural panel. As we'll see on the next slide, plywood is composed of thin sheets of veneers or plies that are arranged in layers. Common veneer thicknesses are 1/6 of an inch, 1/8 of an inch, and 1/10 of an inch. While a plywood panel may have an even number of veneers, it will always have an odd number of layers. This can be accomplished since each layer may consist of one or more veneers in the same grain direction. The grain direction of adjacent layers in a plywood panel alternate direction to maximize the strength and stiffness and minimize shrinking and swelling potential of the panel. If you were to imagine taking a single plywood panel and separating each layer, you would get what's shown here. The arrows mark the grain direction, and therefore strong direction, of each layer, which is alternated between the adjacent layers. The grain direction and the face and back plies of a plywood panel always create the strong direction of the overall panel, typically the long dimension. The cross-laminating process provides strength in this direction and also makes the panel more dimensionally stable and helps to distribute the loads throughout the panel. OSB is built with many of the same principles as plywood. However, rather than composed of veneers, OSB is manufactured of compressed wood strands, which provides an opportunity to make more efficient use of the wood resource. Just like in plywood though, OSB panels have cross-oriented layers, typically 3 to 5. This is accomplished by orienting the strands in the same direction within a layer and provides the same dimensional and structural benefits. If you were to imagine separating out each layer of an OSB panel, it might look something like this. Once again, the arrows mark the grain direction or strong direction of each layer. As with plywood, the grain direction in the face and back layers dictates the strong direction of the overall panel, which is typically the long dimension. The strength axis of an OSB panel is assumed to be along the length of the panel unless marked across the panel. These photos show an example of OSB mat prior to being compressed. Here you can see the individual strands, which have their lengths generally oriented in one of two orthogonal directions, depending on the layer. The strands will keep these orientations as adhesive is applied and the mat is pressed into the final panel thickness. To learn more about a wood structural panel, you'll want to go to the APA trademark stamp. This stamp is your key to understanding the panel's intended use and compliance with industry standards. So let's break down what you'll typically find on an APA stamp. First, you'll see the APA logo. This confirms that the panel has been manufactured under APA's quality assurance program. The second is the panel grade, which indicates the panel's intended use, such as rated sheathing, sturdy floor, single floor, or underlayment. Span rating will tell you the recommended maximum on-center spacing between supports when used for roof or floor sheathing for typical residential loading. For example, A span rating of 32/16 means 32 inches on center for roofs and 16 inches on center for floor supports. The bond classification will either be exterior or exposure 1. Standards compliance will indicate if the panel meets PS1 or PS2. The mill number or manufacturer's code identifies the facility where the panel was produced for quality assurance and traceability. Understanding this stamp helps ensure that you're using the right panel for the right application, meeting building codes and structural performance needs. There are 4 main end-use ratings for wood structural panels. The first is just sheathing, which is for walls, roofs, and floors, providing structural strength. Another is underlayment, which creates a smooth base for flooring materials. A third is single floor or sturdy floor, which is a combined subfloor underlayment, ideal for carpet and pad finish flooring. And a fourth is exterior siding, which are structural panels with decorative, weather-resistant surfaces. All engineered wood products that bear the APA trademark use moisture-resistant adhesives that are known to provide bond quality and strength over time, despite fluctuating moisture conditions. APA trademark panels may be produced to 2 moisture-resistant bond classifications. The first is exterior, which is intended for long-term exposure to wetting, and the second is exposure 1 panels, which are suitable to resist the effects of moisture on structural performance during construction or other conditions of similar severity. We'll discuss these more soon. The structural 1 rating indicates extra cross-panel strength for seismic, wind, and heavy load applications. Struct 1 panels are often used for panelized floor and roof components. Here are 2 examples of APA trademark stamps. The first, on the left, is an example with the PS1 standard specified. This standard is used with plywood structural panels. The second, on the right, is an example of the PS2 standard, which can be used for both plywood and OSB structural panels. Another important piece of the APA trademark stamp is the performance category. Highlighted here in yellow, the performance category does not indicate the exact thickness of the panel, but rather a rounded, approximate thickness aligned with sheathing thicknesses referenced in the building codes and other design literature. Note that the decimal thickness is also declared on the stamp, highlighted here in green. This value is generally at or near the lower tolerance specified in PS1 or PS2. This system helps builders and designers select the right panel thickness for the job while ensuring compliance with industry standards. This slide shows Table 12 from the APA Panel Design Specification, Form D510. The table provides performance category and nominal thickness in inches by span rating. Note that the predominant performance category for each span rating is highlighted in bold type. It's highly encouraged to specify structural applications by span rating or both span rating and performance category, as you may end up with the wrong span rating if you're only specifying the performance category. Surface texture of panels can vary based on the grade of veneers used in the faces and the surfacing process during manufacture. Panels with A, B, and C plugged faces will largely be solid on the surface. C and D grade faces will have some voids in the face veneer. Grades can be chosen based on the intended application of the panel. Plywood panels are often referred to by their face grades. Take CD rated sheathing panels, for example, often referred to as CDX. CD refers to the grade of the face and back veneers of the plywood panel, respectively. Let's take a closer look at bond classification, which can be either exposure 1 or exterior, and relates to moisture resistance of the glue bonds in the panel. The bond classification does not affect the strength and stiffness or span rating of wood structural panels when used as intended. Panels with exposure 1 and exterior bond classifications use the same moisture-resistant adhesives. The quality of the veneers in the panels are what differentiates the bond classification grades. Exposure 1 panels are suitable for uses not involving long-term exposure to weather and can use any of the veneer grades in the layup of the panels. Panels classified as Exposure 1 are intended to resist the effects of moisture on structural performance during construction or other conditions of similar severity. Exposure 1 panels may also be used when exposure to the outdoors is protected from direct exposure, such as the underside of panels at roof overhangs. Exterior panels have bonds capable of withstanding repeated wetting and redrying or long-term exposure to weather or other conditions of similar severity. While Exposure 1 panels permit the use of D-grade veneers, exterior panels must use veneers of C grade or better. Except for APA-rated siding and rated sheathing panels used as wall sheathing, the span rating is based on typical roof and floor loading. Roofs are considered to have a deflection limit of L/240, with a 30 pound per square foot live load and a 10 pound per square foot dead load. The floor span ratings are based on a deflection limit of L/360, 100 pounds per square foot live load, and 10 pound per square foot dead load. There are a few assumptions for the panel span rating that need to be satisfied. The first is that the strength axis of the panel needs to be oriented perpendicular to supports on floors and roofs. This is generally not required for wall sheathing, as walls will not be subjected to the same loads as floors and roof sheathing. The second requirement is for the panel to span across 3 or more members, meaning over 2 framing bays. The third assumption is that the applied panel section is at least 24 inches wide so that the load can be properly distributed across the panel width. There is guidance in Form D510 on use of more narrow panel sections that we will discuss later. APA Technical Note Panel Edge Support for narrow width roof sheathing, Form R275, also gives some prescriptive solutions for narrower panels in roof sheathing and is free for viewing on the APA website. In most cases, the strength axis is parallel to the long direction of the panel. If the strength axis is in the long direction, a strength axis arrow is not required and may not be noted on the panel. The absence of a strength axis arrow marking indicates the strength axis is in the long direction. Some wood structural panel products intended for wall sheathing applications have their strength axis oriented in the short direction of the panel. When this is the case, the strength axis arrow will be shown on the panel. Let's look at the example panel load capacities when we change the roof panel direction over supports. Using APA Table 33 from our Engineered Wood Construction Guide, we see an allowable load of 100 pounds per square foot for a 7/16 category panel with 16-inch on-center support spacing. If we turn the panel so that the strength axis runs parallel with the framing, we'll refer to Table 36 instead and find an allowable live load of only 35 pounds per square foot at a maximum span of 16 inches on center. This is a very significant reduction in load capacity, so it's important to understand how the panels will be installed in the field. Structural 1 panels are manufactured with Group 1 veneers in all plies, and those veneers have additional limitations on splits, knots, and knot holes. This gives the Structural 1 panels increased strength in the direction perpendicular to the panel strength axis. I'll showcase the adjustment for this later on. When designing the wood structural panels, it's important to know where to find the right reference values for panel stiffness and strength. NDS Section 921 makes it clear. These values must come from an approved source. The commentary for NDS Section 9.1 explains that Chapter 9 provides only the basic engineering design requirements for wood structural panels. For more specific details, you'll need to refer to the manufacturer or a qualified agency such as APA. The American Wood Council's Special Design Provisions for Wind and Seismic, commonly known as SPDWIS, also makes extensive reference to APA's panel design specification in their sheathing commentary. In most cases, wood structural panels can be specified without needing to perform an engineering analysis. They're already tested and rated for typical applications that we've shown on the APA trademark. For typical projects, this system makes it easy to select the right panel for the job. However, there are times when engineering design is necessary. This could be when a project requires specific panel properties or capacities beyond standard ratings. In the following slides, we'll explore how to use APA's Form D510 for an engineered design. This session is based on the most recently updated edition of D510, released in 2020. This publication is scheduled for update in 2026. Section 4.4 of the panel design specification provides background information on each of the capacity types, such as variable definitions, testing procedures, units, derivation processes, and direction on how to obtain allowable stress values. The section also provides figures to help the reader distinguish between different panel loading directions and shear types. We'll start with panel flexure for flatwise panel bending, which can often control design. Panel bending stiffness is the capacity of the panel to resist deflection and is represented in bending equations as EI. The E is the apparent modulus of elasticity of the material, which means it is intended to account for effects of both bending and shear deformation. I is the moment of inertia of the cross-section of the panel per foot of panel width. Units of EI are in pound-inches squared per foot of panel width. On this slide, we're looking at the panel's allowable flatwise bending strength capacity. This value corresponds to the maximum moment the panel can safely resist in design, and it's measured in pound-force inches per foot of panel width. Again, it's important to note that the bending performance depends heavily on the orientation of the panel relative to the strength axis. The next design capacities are the axial strength and stiffness characteristics of structural panels, which include both tensile and compressive capacities. F sub T is the allowable tensile and F sub C is the allowable compressive stress of the panel. The A term in each capacity is the cross-sectional area of the panel for a 1 foot width. There are two types of shear strength for wood structural panels: in the plane of the panel and through the panel thickness. Shear capacity in the plane of the panel is the capacity to resist horizontal shear forces when loads are applied or developed on opposite faces of the panel, as they are during flatwise panel bending. The graphic on the left of this slide helps visualize this loading within the panel. A panel's shear capacity through the thickness, sometimes called in-plane shear capacity in lateral load design, is the capacity to resist horizontal shear forces when loads are applied or developed on opposite edges of the panel. This is the case for wood structural panel webs on an I-joist and for in-plane loading of sheathing on a braced or shear wall. Panel shear rigidity through the panel thickness, sometimes called in-plane shear rigidity in lateral load design, is a panel's capacity to resist deformation when under shear through the thickness stress. Panel shear rigidity is represented by G sub V T sub V, which is the product of the modulus of elasticity and the panel thickness. The units of G sub V T sub V are pounds per inch of panel depth for vertical applications. Shear bearing capacity and the allowable bearing stress of wood structural panels may come into play for some design conditions. As compression load is applied perpendicular to the plane of the plies, or to the surface of the panel, such as by a column or reaction at supports, bearing stress is induced on the panel through the bearing area. A design bearing stress of 360 pounds per square inch shall be used for wood structural panels under dry use conditions, or when the moisture content is less than 16%. This design is based on an applied test loading at a 0.04 inch deformation limit. If a stricter deformation is required for the design, design bearing stress can be chosen at 210 pounds per square inch, which correlates to a 0.02 inch deformation limit. For more information on the design bearing stresses of 360 and how it was determined, see APA Technical Topic 001, titled Allowable Bearing Stress for APA Wood Structural Panels. APA Form D510 provides guidance on reference fastener design values in Section 448. Subsections address the determination of nail withdrawal, wood screw withdrawal, fastener head pull-through, and fastener lateral design values. For wood structural panel design, the equivalent specific gravity, or ESG, of the wood structural panel replaces lumber specific gravity in the NDS equations. This slide shows Table 4 in Form D510, which provides equivalent specific gravity, or ESG, for various combinations of loading mode, fasteners, and panel types. The reference nail withdrawal design values for wood structural panels may be calculated with these two equations provided in Section 4481 of APA Form D510. As a reminder, the same equations are also provided in Section 1223 of the NDS. Equation 1 is used for smooth or screw shank carbon steel nails, and equation 2 is used for ring shank carbon steel nails. Units of W are in pounds per inch of penetration. The reference nail withdrawal design values need to be multiplied by all applicable adjustment factors. For ease of reference, the calculated reference nail withdrawal design values are tabulated in tables A1 and A2 of Appendix A in Form D510. Reference withdrawal design values for wood screws from wood structural panels depend on several variables. They may be estimated with equation 3 shown here and found in Form D510. The NDS provides the same equation for this condition. We can again use the ESG values listed for wood structural panels in Table 4. Units of W are pounds per inch of thread penetration and need to be multiplied by all applicable adjustment factors. Calculated reference wood screw withdrawal design values are also tabulated in Table A3 of Appendix A of Form D510 for ease of reference. Proprietary fasteners may have their own published data. A nailed or screwed sheathing to wood joint may be limited by either fastener withdrawal from the lumber or by fastener head pull-through strength of wood structural panels. Equation 4 or 5 may be used to estimate fastener head pull-through design values. Which equation is used depends on the ratio of the panel thickness to the fastener head diameter. Equation 4 is used when wood structural panel thickness is less than or equal to 2.5 times the fastener round head diameter. If the wood structural panel thickness is more than 2.5 times the head diameter, equation 5 is used. Units of W are pounds and the value needs to be multiplied by all adjustment factors. Calculated reference fastener head pull-through design values are tabulated in Appendix B, Table B1 for ease of reference. Reference lateral design values for dowel-type fasteners installed on structural panels shall be calculated using the dowel bearing strength of wood structural panels provided in Form D510, Table 5, and the yield limit equations provided in Table 1231A of the NDS. Chapter 12 of the NDS provides calculated reference fastener lateral load design values for many common conditions. Units of Z are pounds and the values need to be multiplied by all applicable adjustment factors in the NDS in Form D510 Section 4.5. This is Table 5 from Form D510. Note that the dowel bearing strengths are different for fasteners less than or equal to a 1/4 inch diameter versus those between a 1/4 inch and a 1/2 inch diameter. The bearing strength also differs depending on if the load is applied parallel or perpendicular to wood structural panel strength axis. For dowel fasteners between 1/2 inch and 3/4 inch in diameter, refer to APA Technical Note, Fastener Loads for Plywood, Bolts, Form E825. NDS Table 1231 is shown on this slide. All of these equations would need to be completed and the reference lateral design value would be the minimum value computed. This is clearly a computationally intensive process, so for ease of reference, Chapter 12 of the NDS provides the calculated reference fastener lateral load design values for various fastener types, configurations, and framing and sheathing materials. Reference lateral fastener design values, specifically for single shear connections of saw lumber or SCL to wood structural panel side members, are tabulated in NDS tables 12Q and 12R. With each of the design capacities, we talked about adjusting the reference design values by the applicable adjustment factors. So what exactly are those factors? These factors account for the duration of the load, creep, service moisture conditions, elevated temperature, pressure treatment, panel size, and certain panel edge support conditions. These factors are described in detail in section 4.5 of Form D510, and we'll review them briefly. Design capacities listed in Form D510 are based on normal duration of load. Table 6 lists the duration of load adjustment factors for other times under load. They are like what's given in the NDS, but note that adjustment for impact load does not apply to wood structural panels. Wood structural panels under constant load will creep over time, or in other words, deflection will increase. For typical construction applications, panels are not normally loaded under constant load, and therefore creep does not need to be considered. When panels will sustain permanent loads that will stress the product to 1/2 or more of its design strength capacity, allowance should be made for creep. In these cases, the creep adjustment factor may be applied to panel EI value used in deflection calculations. The adjustment factors are provided here in Table 7 from Form D510. Reference design capacities in Form D510 apply to panels under moisture conditions that are continuously dry in service. That is where equilibrium moisture content is less than 16%. Adjustment factors for conditions where the panel moisture content in service is expected to be 16% or greater are shown in Table 8 of APA Form D510. Design capacities noted in D510 apply at temperatures of 70 degrees Fahrenheit and lower. Wood structural panel parts of buildings should not be exposed to temperatures greater than 200 degrees for more than very brief periods. Between 70 and 200 degrees, adjustments generally do not need to be made. While temperatures of up to 150 degrees do occur under roof coverings on hot days, they are generally accompanied by moisture content reductions that increase the strength of wood structural panel and offset the loss due to higher temperature. The designer should exercise judgment on if high temperature and moisture conditions will occur simultaneously to determine if temperature adjustment factors should be used. Wood structural panels are sometimes pressure treated for added fire and moisture resistance. Capacities in D510 do apply without adjustment to plywood pressure impregnated with preservative chemicals and re-dried in accordance with the American Wood Protection Association Standard U1. However, the capacities in D510 do not apply to fire retardant treated structural panels. Capacities and end-use conditions should be in accordance with the recommendations and model code evaluation reports of the company providing the treating and re-drying service. See APA Technical Note, Fire Retardant Treated Plywood, Form K320 for additional information. Bending and tension strength capacities noted in D510 are appropriate for panels 24 inches or greater in width. For panels less than 24 inches in width, where failure could result in life safety concerns, a panel size adjustment factor, C sub S, shall be applied to the panel bending and tensile strength capacities as noted here. B is the panel width or dimension perpendicular to the applied stress in inches. For roof sheathing applications, additional panel edge support is recommended when panel widths are less than 24 inches. Specific recommendations are an APA technical note, panel edge support for narrow width roof sheathing applications, Form R275. Let's get started with our first design example, assumed to be for a project located in White Pass, Washington. To find the ground snow load for this location, we'll go to ASCE 7, Table 7.2-5, which is titled Ground Snow Load for Select Locations in Washington. We find the ground snow load for White Pass to be 244 pounds per square foot. For a real-world design, we would need to consider several modifying factors that impact how the ground snow load is converted into the actual roof snow load. These include things like exposure factor, thermal factor, importance factor, the slope of the roof, and unbalanced loading and drift conditions. Since this roof snow load derivation is not the focus of this webinar, we'll simply assume the roof snow load equals the ground snow load. This, of course, is an extremely high snow load, but we want to illustrate how panels may be designed for conditions far outside typical span and loading conditions. We're using allowable stress design, or ASD design, so the relevant load combination from ASCE 7 is dead plus snow. We'll assume dead load is 10 pounds per square foot, so the total design load is 254 pounds per square foot. Now let's apply the APA panel design specification, Form D510. For this example, we're assuming the roof framing is spaced at 24 inches on center. The framing members are 3 by or greater in width, which affects how APA assigns strength values. We're using a duration of load factor of 1.15, intended for load durations of up to 2 months. It's important to note that the duration of load factor applies to bending and shear strength, but not to deflection. The deflection limit we're using is L over 240, per the IBC requirement for roof sheathing. We're evaluating 1 1/8 performance category OSB sturdy floor panels with a span rating of 48 inches on center. The flexural stiffness value is 1,150,000 pound-inches squared per foot of panel width. The bending capacity is 1,900 pound-inches per foot of panel width. And finally, the shear capacity in the plane of the panel is 385 pounds per foot of panel width. The panel properties are all found in Table 9 of APA Form D510. To find these values, we first find the span rating of the panel we're using in the left-hand column of the respective design capacity we are seeking. We then traverse right in that row to the appropriate panel type, noted at the top of each column. The values may vary for OSB versus plywood, and may also depend on the number of plies for plywood panels. If you don't know what will be used, one option is to assume the more conservative value between the options. The values we noted for our assumed panel with a 48-inch on-center span rating are circled in red. The equations shown on the right are provided in section 474 of Form D510 and are used for computing allowable uniform loads based on designed bending strength capacity of a panel. Different equations are given for 1, 2, and 3 span conditions. While it's common to specify 2 span minimum, both 2 and 3 span conditions will likely occur on site, so you'll want to verify the worst case. For bending strength, the L sub 1 span value is simply the center-to-center spacing of supports. After inputting our adjusted design bending strength capacity and sheathing span into the equations for both a 2 and 3 span condition, we find a minimum uniform load of 364 pounds per square foot, which is greater than the applied 254 pound per square foot loading. Therefore, our chosen panel is adequate in bending strength. The equations shown on the right here are provided in section 475 and are used for computing allowable uniform loads based on the shear strength of the panel. Once again, different equations are given for 1, 2, and 3 span conditions. L sub 2 in these equations is not just the center-to-center spacing of supports. Instead, we subtract the support width from the support spacing to get our clear span. We input our clear span and adjusted design shear strength into the equations for both a 2 and 3 span condition and find a minimum allowable uniform load of 395 pounds per square foot, which is greater than the applied 254 pound per square foot loading, meaning our chosen panel is adequate. The last gravity loading check we need to do concerns deflection. The equations shown on the right are provided in section 476 and are used to calculate allowable uniform loads based on deflection requirements. The equations differ for the number of spans. It's assumed that an equal uniform load is applied to all spans. We first find our allowable deflection in inches by dividing our span by 240, which gives us 0.1 inches. Note that the L in these equations is not simply the clear span of the panel. Rather, it is the clear span plus an SW factor, which depends on the width of the framing supporting the panel. Factors are given for 2 and 4-inch nominal lumber. Since we assumed a 3x or larger framing member for this example, we'll use the more conservative 0.625 value for SW in our calculations. We then enter our uniform load, L value, and the panel design bending stiffness that we found in Table 9 into the equations for 2 and 3 span conditions. We find a maximum deflection of 0.029 inches, which is less than the 0.1 inch limit, so our panel passes for deflection. Fortunately, all those calculations may not always be necessary every time you need to design a panel, thanks to APA Form Q225, load span tables for APA wood structural panels. These load span tables apply to APA trademarked wood structural panels qualified and manufactured in accordance with PS1 and PS2. Note that for panel strength axis perpendicular to supports and spans of 32 inches and less, a 3-span condition is assumed for the panel. A 2-span condition is assumed for spans greater than 32 inches. Effects of support width have also been considered when determining the loads based on shear and deflection. Supports are assumed to be 2-inch nominal members for spans less than 48 inches and 4x for members for 48-inch or greater panel spans. One final note about these tables is that they assume normal load durations. For these reasons, the values highlighted differ from those we calculated in our first example. However, if our design conditions match those assumed for these tables, they provide a quick reference point. Let's move on to our second and final example. In example 2, we'll evaluate wall sheathing for a typical home in Miami-Dade County, Florida, where the local building department indicates an ultimate wind speed of 170 miles per hour. Wind design is complicated, and a lot of different factors can play into the design pressure. The focus of this session is on the design of the wood structural panel, so we'll skip that derivation and assume a design wind pressure of 41.8 pounds per square foot. Let's walk through how to calculate allowable pressure using Form D510. For this example, we'll use 7/16 category OSB, struck 1 rated, with 24/16 span rating. We're assuming wall framing is spaced at 16 inches on center and using SPF lumber. The framing members are 2x or greater in size. We'll also assume that the wall will have an exterior stucco finish, which will dictate our allowable deflection. The duration of load factor, C sub D, is 1.6 for short-term load durations of 10 minutes associated with wind loads. It's important to note that the duration factor applies only to bending and shear capacities and not to deflection. We'll reference Form D510 to determine the base allowable stresses for the panel type, then apply C sub D and any other relevant adjustment factors. From there, we can calculate the allowable uniform pressure the panel can resist based on span and loading conditions. This process ensures that both structural strength and serviceability, such as deflection limits, are checked appropriately based on real-world use conditions. We locate Table 2B in APA Form Q225, which tabulates uniform loads on APA-rated OSB struck 1 sheathing, assuming multi-span and normal duration of load. We'll use the conservative design values for sheathing parallel to supports on the right side of Table 2B. If we are trying to stick with a certain panel type and stud spacing, but the parallel to support capacity wasn't adequate, note that you could consider specifying that the panel strength axis be installed perpendicular to take advantage of the much higher allowable loads, boxed in red. The table provides different load capacities depending on what may govern: bending, shear, or deflection. There are 3 deflection criteria in Table 2B that correspond to the 3 allowable deflections listed for exterior walls in the IRC. We assumed an exterior stucco finish in our design, which limits our deflection to L/360. Since the table is based on normal load duration, we can increase the allowable bending and shear loads by 60% for wind. We find that the panel is easily adequate for bending and shear and narrowly passes for the deflection limit. We now know the panel strength is adequate, but we also need to verify that the panel is adequately attached to the framing. After all, the panel strength doesn't count for much if it's no longer on the structure. We'll assume the fasteners are 8D sinker nails and initially assume an intermediate nail spacing of 12" on center. We assume a specific gravity of 0.5 as specified in D510 for struct 1 OSB. We then obtain the length, diameter, and head measurements of the nail from table L4 in the NDS. We then move to equations 4 and 5 provided in section 4483 of D510. Since the panel thickness T is less than the head diameter of the fastener D sub H multiplied by 2.5, we use equation 4. Entering the fastener head diameter and equivalent specific gravity and thickness of the panel into equation 4, we get a reference fastener head pull-through design value of 100 pounds. We find the tributary area of each fastener by multiplying the spacing of studs, 16 inches, by the spacing of intermediate or field fasteners, 12 inches, and then converting to square feet. We get 1.33 square feet of tributary area for each fastener in this case. We can then find our allowable pressure on the panel by dividing the nail head pull-through by the tributary area. We find an allowable pressure of 75 pounds per square foot, which is greater than our imposed pressure of 41.8 pounds per square foot, so the assumed panel fastening is adequate. We still have one more mode to check to verify our sheathing is adequately fastened to the framing. We need to consider nail withdrawal from the framing. Equation 12.2-3 from the NDS may be used to find the reference withdrawal design value in pounds per inch of smooth shank nails. To get the withdrawal capacity of the nail, we would multiply this W value by the length of the fastener penetration, P sub T, into the framing. Alternatively, we can use table 12.2C in the NDS, which tabulates the withdrawal design values. For a shank diameter of 0.113 inches and a specific gravity of 0.5, we find a withdrawal design value of 28 pounds per inch of fastener penetration. Multiplying this value by the depth of the fastener penetration into the framing and our load duration factor of 1.6, we determine a withdrawal capacity of 86 pounds for each nail. Dividing 86 pounds by our nail tributary area of 1.33 square feet, we get an allowable pressure of 64 pounds per square foot, which is larger than our imposed pressure of 41.8 pounds per square foot, so the assumed panel fastening is also adequate for its withdrawal from framing. This mode can often control design. If we didn't have enough withdrawal capacity, some options to consider are tighter intermediate fastener spacing, longer or larger diameter nails, or the use of different fastener types such as ring shank nails. It's important to note that some wood structural panel applications are not controlled by uniform loads. Residential floors are a good example. They are commonly designed for 40 pounds per square foot live loads. The calculated allowable uniform floor load on panels applied at maximum span according to APA floor span ratings is greatly in excess of typical design loads. This excess does not mean that floor spans for wood structural panels can be increased, but only that there is considerable reserve strength and stiffness for uniform loads. The recommendations for floor panels are based on performance under concentrated loads, how the floor feels to passing foot traffic, and other subjective factors that relate to public acceptance. Always check the maximum floor and roof spans for wood structural panels before making a final panel selection for these applications.
Okay, thank you, Noah. So before we begin our Q&A, I'd like to remind you that your feedback on today's webinar really counts. The QR code shown on the screen will link you to today's survey. Just open the camera on your smartphone and a link will take you to the survey. A link will also be emailed to you in about an hour. Please take a minute and fill that out. So we only have a short time left, but let's get to a couple of questions that came in. And I'll also remind you that if we don't get to your question, we're going to have a local engineered wood specialist reach out to help. Okay, first question. Where can I get the APA panel design specification?
The panel design specification is available on the APA website. Just like most other APA publications, there's a PDF format that can be downloaded for free from our website, apawood.org. To download, you do need to first register on the website and then click on the confirmation link that gets sent to your email. But once you do that, you can go to the APA website and there will be a search bar on the upper right-hand side where you can type D510 or panel design specification in that search bar, and a link will come up for you to click, and that will download the PDF version of Form D510 for you.
Okay, thanks, Noah. Next question. What information needs to be included in panel specification on project plans and notes?
Good question. There's a lot of information in that APA trademark. You'll generally want to include as much information as possible in your specification to make sure you're getting the right panel that you're intending. The APA panel grade, span rating, bond classification, performance category, those are probably the most essential things to include. Our engineered wood construction guide, which is Form E30, gives a little bit more of a detailed guidance on how to properly specify and order wood structural panels. So if you want to make sure you're including all the possible things that you can, go to the engineered wood construction guide and check out that panel specification page.
Great. Okay, I think we will have time for one more question and then we'll need to move on. So where can I get FRT or fire retardant treated panel design values?
So as we talked about earlier, the D510 design specification does not provide design values for fire retardant treated panels. Those would need to come from the third party that's doing the fire retardant treating. So you need to reach out to that manufacturer or check their website and literature for some possible adjustments or different listed design values. So those would not come from the APA member company or from APA. They'd have to come from the FRT treater.
Okay, thank you, Noah. Again, if anyone has additional questions, please feel free to reach out to your local engineered wood specialist after the session. So this slide and the next are going to provide QR codes for each of the APA publications that were referenced in this session. You can use the camera on your smartphone and a link will take you to the APA webpage to download the respective publications. These are included in the handout for your use. As I mentioned, APA has field staff located throughout North America. Your local APA engineered wood specialist is a free resource that's available to assist you on any questions that you may have regarding APA engineered wood products. Their individual contact information can be found on the staff contacts page of the APA website. To navigate this page, you can go to apawood.org, select Contacts at the top. This is going to take you to our main contact page. If you select the Learn More option under Market Access and Development, you'll navigate to our Engineered Wood Specialist page with a map showing the different territories where we have field staff. And by scrolling down, you can select the appropriate region and get the contact information for your local Engineered Wood Specialist. And finally, make sure that you're signed up to receive our APA Update newsletter. so that you will be notified of our next webinar, as well as future webinars and updates to APA publications and standards. To receive it, all you need to do is, starting from the home page of our website, click on Sign In the upper right-hand corner of the page. In the menu that drops down, simply select Register. From there, you need to let us know what you'd specifically like to receive, which in this case is the APA Update newsletter. Additionally, APA has resources to assist you at our help desk that can be reached through email at help@apawood.org or phone at 253-620-7400. Thank you all for attending.